I'm going to talk about data compression. I'm going to mention the dreaded word neural networks. I'm sorry about that, because what I'm essentially going to do is talk about what people do now rather than what anybody might think they ought to do, or any sort of rights or wrongs of using. Rights or wrongs of using AI. So I'm not going to present my own work because I've been looking at data compression in the context of higher order weak lensing statistics, but I don't feel I'm quite ready to share what I've done. So I'm just going to talk about methods and why you might consider different methods in different circumstances. Right, well, I'll go from here. I just showed two papers that I have used, both of which describe and compare data compression methods. But what I'm really talking about is moving on, like Marie just said, from the most recent surveys, legacy surveys, to what we do next. And I'm going to talk about why data compression might matter in that context. And this is a huge, can I not do it on this one?
No, it's just. What if you share your entire screen? May I share your entire screen? Okay, transmission. Okay. Yeah, it's recording. Okay.
So thank you. Fingers crossed. Right, so this is an enormous generalization, simplification. But what you do, what has been done often in the legacy surveys is you construct a two-point statistic, which Marie talked about. You make some assumption about the likelihood, and often you assume it's Gaussian. Then you do an MC and get to your parameter constraints, and that all works really well, as we've seen. But we need to move on from that and look at non-Gaussian statistics, because we know the universe isn't Gaussian at late times at small scales. And that points to using higher order statistics. And there are lots of these. I won't go into them. Other people are going to talk about them later. But the main point to make about these is they're significantly more complicated than 2 points, of course. And some of them are quite analytically difficult to deal with. So that's one way in which we're moving on. The other thing we might want to do more of is combine probes. And again, KISS is a good example of the 3 times 2 point weak lensing analysis. But you can also obviously combine different probes. And I think we're going to do this more and more, combine lensing, CMB, BO, void, etc. And I found this nice paper that actually combined 12 2-point statistics, which is interesting. And the easiest thing to do would be to say, oh, well, they've got this pipeline. I'll just put my new statistics into that and proceed as before. But that isn't really viable because you've got a problem with the likelihood, because you really can't assume it's Gaussian anymore. In fact, in many cases, you don't know what the likelihood is at all. So that is causing many people to move away from this to a dreaded neural network-based method, simulation-based inference. And the key point about this is you don't have to know what your likelihood is in advance. You learn it from a neural network with a neural network. So what you have to do is forward model your data or simulate it, create summary statistics as you choose, feed it into a neural network, and it learns the likelihood. And once you've got a trained model, you can then take your data, pass it through the same process, and then do your inference. But one issue with this is that even if you've got a very large number of simulations, the neural network may struggle to learn the likelihood because you may have a data vector which is hundreds of elements long. And so it's very common to add a data compression step here. And that will be a very massive data compression often, down from hundreds down to only a small number, a very small data vector. And that's easier for the neural network to cope with. And after that, you can proceed as before. But one thing you might ask is, by doing this data compression, are you not losing information about your parameters? And obviously, that is something that's undesirable. You could also worry that it's making your pipeline even more complicated. So I suggest there's 3 things we might think about when doing data compression. First of all, you want to obtain as much information as possible, as I've said, and I'll come back to that. Then you want to do something practical. You don't want to put a really complicated process in which isn't necessary. But on the other hand, you don't want to oversimplify things so you lose some of the subtleties of the data. And finally, you've got to do it in the principled way. You've got to be able to justify why you did it in the way you did it. And I think increasingly that those sort of questions have to be answered if you're going to compress the data. In fact, they already should be. So now I'm going to come back to what we mean by retaining as much information as possible. And in one sense, this doesn't really matter, because if you have a bad compression, you don't bias the results, you just get wider contours in the end. But obviously, it's better not to do that. It's better to retain the information. So what do we mean by retaining as much information as possible? And in statistics and widely in cosmology, there is a commonly used definition of information, which is a Fisher, basically it's Fisher matrix, which depends on the data covariance and the derivatives of the data with respect to the parameters. If there is a theoretical best way to compress while conserving Fisher information, that's compression to the score, which is the derivative of the log likelihood with respect to the parameters. That's not possible in most cases because you don't know the derivatives, you don't know the likelihood. So other methods are commonly used, and the most widely used one is MOPED, which people have probably heard of, where you assume you've got a Gaussian likelihood, you assume the covariance doesn't depend on the parameters, it reduces to a linear problem, and it's fairly straightforward to proceed with that. And the other thing you can do is say, well, actually, I don't want to make any assumption about the likelihood being Gaussian, but you can still do a maximization, finding a function which maximizes the information, the Fisher information retention, using a neural network, and that's called information maximizing neural network, and it has been used in cosmology. It's complex. Both these methods are complex because they require derivatives, that they are feasible. Now, if your likelihood is definitely not Gaussian, you can still proceed. You can use a different definition of information, which is mutual information, which is a information theory concept, which I won't go into, but essentially it's a global measure of the difference between two distributions, whereas Fisher information is a local information looking at curvature around the maximum likelihood. So this is a global method. You can set up a new loss function based on mutual information, and that too has been used. And finally, those are all sort of fairly principles. We've defined what we mean by information. 2 other methods. One is commonly used, the other is new to me, but I will describe it. Very often, people use this very simple, a neural network, which compresses down the data, but minimizes the loss function based on the difference between the predicted and the actual parameter values. And this is fine, but it isn't guaranteed to maximize any sort of information unless you've got a nicely behaved posterior. And the final method I'm going to talk about is called canonical correlation analysis. And that was referenced in that paper, which I couldn't show before, which is by Park et al., who compared methods. And they introduced to cosmology, I think, this concept, which is essentially a generalization of principal component analysis, which looks for linear combinations of the data which maximize correlations between 2 data sets. And in our case, it's between the compressed data and the parameters. If the data are Gaussian, it becomes a bit more like mutual information. But This is just a little eigenvalue problem. So it's really easy to do. Doesn't require neural network, doesn't require any derivatives. So it'd be nice if we knew it worked. And in their paper, this is just one plot from their paper where they compressed some weak lensing data, higher order statistics. And they actually found that CCA did better than some of the other non-linear or more sort of principled methods, which is interesting because if it could use that, then it would be a very quick and easy way to do the compression. And so I'm finished. I will leave you with the conclusion, which I don't really need to read out, but I think it's, if we're going to use simulation-based information, then, and we've got all these very big complex data sets, then we will need to compress the data. It might matter, or at least you ought to think about how you do it. It might be very much dependent on it, particular setup you've got, so no general rules, and it's always going to be a balance of practicality and principle. Thank you.
And thanks for being on time. Is there any question, Susan? Yes.
Thanks, Susan. I wanted to ask you, you said you can't talk about what you're doing, but can you tell us like a little bit about this?
Well, I was essentially, this paper by Park et al. Sort of appeared while I was doing the work already. I'm not getting the same, so it's rather similar to them, but I'm comparing more different methods and a slightly different statistic. And I'm not getting quite the same results they were getting, this conclusion about CCA. So I'm sort of revisiting because I would like to know whether CCA works. And ideally, it would be nice to experiment with more different statistics to see what difference they make.
Okay. And so you don't find that this, what's it called, the last method doesn't work as well as what they found?
I don't find that, but it needs looking at. Really, they didn't really explore what it was about their data and their setup that gave them the good results. And it's possible that if your sort of data and parameters were fairly linearly related and maybe other criteria met, you can guarantee that will do better. But I'm not sure.
Yes. Okay.
Maybe one more question. Okay, if not, we can say thanks again.